Hey there, class. Mr. Prusky here. Hope you're having a good day so far. We're continuing with a new chapter today. Today is chapter 7, and chapter 7 is powers, roots, and radicals. Today is section 7.1, and the name of this lesson is nth roots. Actually, the name of this lesson is nth roots and rational exponents. That's the actual name of the actual section, but the essential question is, how do we rewrite rational exponents as nth roots? Are we able to evaluate expressions with rational exponents? And can we work with these without a calculator? Okay, so I don't know if I probably have mentioned in class so far when we've been talking about taking the cube root of something. The way we take the cube root of something, so for example, if I want to do, oops, that is a very thick marker. Let's fix that. So when I wanted to do the cube root of 8, for example, well, what is the cube root of 8? What times itself 3 times is 8? Well, it's 2. But the way you do that on a calculator, there's kind of a shortcut. The way I kind of tell students to do that is you take 8 to the power of 1 divided by 3. Okay? So a cube root is the same thing as the 1/3 power. So you've actually been working with nth roots and rational exponents before. It's just we haven't really talked about it explicitly yet. So basically, the way this works is that the root, whatever root it is going to be the denominator of the exponents, and the exponent's going to go on the top with the normal exponent. So for example, if we had, let's see here, if we had the 6th root of x to the 5th, that'd be the same thing as x to the 5/6. Okay? So the exponents under the radical are going to be the numerator of the fraction of the rational exponent, and the denominator is going to be the index, it's called, which we'll talk about in a second here, okay? But so rational exponents are basically just talking about the exponents, which are the normal things we usually talk about, which goes on top in the numerator, and then the roots go in the denominator, which is going to be the index. Okay, let's get into it here though. So we have the nth root of a. So what I want you to write right here is we're going to use our perfect card. Okay, this is going to be very important to use our perfect card for this section. All right. So what's under the radical is going to be called the radicand. The radicand, we've probably talked about that before. Hopefully you've heard that, but if not, that's okay. And the n is what's called the index. Okay, so the root, whatever power you're taking, whatever roots you're taking, that's going to be the index. All right, so we have the 4th root of 625. Well, that is, what number times itself 4 times is 625? Well, that's going to be 5, because if we multiply 5 by itself 4 times, that's going to equal 625. So the 4th root of 625 is 5. All right. The cube root of -8, well, we couldn't take square roots of negative numbers because then we'd have to use imaginary numbers, but the cube root, actually, we can do the cube root of 8. So what's the cube root of 8? That's 2, right? But in this case, we have a negative. Well, let's take a look at this. If I do -2, let's try -2. Does that equal -8? It does. We didn't break any rules there, really, because the cube root is an odd number. It's an odd number, basically. So it doesn't matter if it has a positive or a negative. So the cube root of -8 is going to be -2. Okay? So kind of going to what we were talking about before, it's the 625 would be 625 to the 1/4 power, and down here this would be -8 to the 1/3 power. Okay? So that's what we have to do for that. All right. It's kind of hard to zoom here. Sorry about that. Okay, next thing we have is the definition. So let's change our color here. Let a to the m over n be the nth root of a, and m be a positive integer. So we have a to the m divided by n. That's going to equal, like I talked about before, the n is going to go in the root, and a to the mth is going to be our normal exponent. Another way you could write this is you could just write in parentheses, write the nth root of a, and you could take parentheses and put the m, the exponent outside too, because that's like, that's power to a power. So the m could go here, or the m could go outside the parentheses. And I'm going to put a star over here. It's important to know, I'm going to put you choose. Sometimes it makes more sense to use one over the other. Okay? And another kind of variation of this, let's write that down for a second. If we have a to the negative m over nth power, that's going to be the same thing as, well, a negative exponent needs to move to the denominator if it's in the numerator, or in the denominator to the numerator if it's in the denominator. So this is going to be 1 over, it's going to be a to the m all to the nth power. Or, like I said before, we can put 1 over in the new parentheses, the nth root of, the nth root of a, all to the nth power, like that. And in this case, m cannot equal 0, because if we have m equals 0, it's going to be a problem. You can't have 0 in the denominator. Okay? All right, let's get into some examples now. So, examples 1 through 3, all we're doing is just rewrite the expression using rational exponent notation. So that means we're taking the roots and the exponents, we're writing it as a fraction exponent, a rational exponent notation. Okay? So we have 14 to the 5th power, or sorry, to the fifth root of 14 is what we have here. So the 5th root of 14, well, 14 is not to any power, so if there's no power there, it's going to be to the first power. And then the 5th root is going to go down here, and that's going to be 15. So the 5th root of 14 is the same thing as 14 to the 1/5 root. All right, why don't you go ahead and see if you can try the other two on your own, 2 and 3 on your own. Give it a try. All right, sounds good. Let's give it a try here. So we have the cube root of 5 squared. So that's going to be the same thing as 5. The exponent goes on top, and the cube root is going to be the denominator of the rational exponent. So we have 5. So the cube root of 5 squared is the same thing as 5 to the 2/3 power. All right, number 3, we have the 4th root of 31 all to the 5th power. Well, in this case, the exponent, like I said, is going to go in the numerator of the rational exponent. So 31 to the 5th, and then the root's going to go in the denominator, which is going to be 4. And there we go. All right, let's go the opposite direction now. So in this case, we have a rational exponent notation, and we're trying to rewrite it as in radical notation. So we're trying to go the opposite direction. Instead of taking taking a radical and going to a rational exponent, we're going the opposite direction. So in this case, well, what I see in the denominator is 6. So I'm going to put the 6th root, because the denominator is the roots and the top is the exponents. Then I have 8 to the 1st power. Well, I don't really need to the 1st power. I could put 8 to the 1st power if I wanted to, or I could just do, I like to simplify things. 8 to the 1st power doesn't really do anything, so you can just write it as the 6th root of 8 would be the same thing. Okay? All right, why don't you see if you can do 2 and 3 on your own. Give it a try. All right, we have 14 to the 5/7 power, so it's going to be a 7th root. We have 14 to the 5th. Or I can rewrite this the other way. Remember, we can rewrite it with the 5 outside the parentheses. So I'm going to write parentheses 7th root of 14 all to the 5th power like this. Either way would be totally fine. And sometimes it makes more sense to do one or the other depending on how you're trying to solve. All right, number 3, we have 9 to the 2/5 power. So it's a 5th root. And it's going to be 9 squared. And we could rewrite that if we wanted to, but you'll get the same idea. You could rewrite this if you want to. We'll do it, why not? We have the 5th root, and we have 9 to the 2nd power like this. Either way would be totally fine. All right, moving on. It says evaluate the expression with a calculator and use the X root key. All right, it depends what kind of calculator you're using for this. So in this case, so you don't even need to use that nth root. What you could do, you could use it if you wanted to, but what I would probably do, I think this is going to be a little bit easier, is just do, if we have the 7th root of 245, do 245 to the power of 1 divided by 7. And that's going to give you the same thing as doing the 7th root. I would just get in the habit of just doing to the power of, the rational exponent like that. It's going to make it a lot easier. So if we do that, we're going to get approximately 2.194. So 2.194 times itself 7 times is going to be pretty close to 245. Okay? Why don't you see if you can try the other two on your own here. Give them a try. All right, so this one we have negative 72 to the power of 3 over 5. Make sure you use parentheses when you're doing that. 3 divided by 5. So this is going to be equal to approximately, if you plug that into your calculator correctly, about negative 13.014. Okay, so this right here, that line is a division symbol. So you do negative 72 to the power of 3 divided by 5 in parentheses. All right, last one, we have 12 to the negative 2/3. So that's going to be the same thing as, let's just do 12 to the negative 2/3. 12 to the power of negative 2 divided by 3. And we're going to get approximately, when we do that, 0.191. And that number is a little smaller because a negative exponent moves to the denominator. So this is the same thing as 1 over 12 to the 2/3. Right? Because it moves, negative exponents move to the denominator like that. So that's why it's a little bit of a smaller number. Okay, let's move on here. It says evaluate each expression without a calculator. So this one's going to be, we're going to have to do some tricks here. We'll see how we do. Let's see how we do. All right, so first things first. Number 1, we have the 4th root of 16. Well, that's 16 to the 1/4, but the 4th root of 16 is an actual nice number, which is going to equal, we should just know that it's going to be 2. And if you had your perfect card, it would also tell you that. Easy peasy. All right, number 2, we have 9 to the negative 1/2 power. So let's rewrite this with radicals. It's going to make it easier to see. So we're going to have the square root of 9 all to the negative 1st power. All right, we can put a square root here if we want to, if it helps with that. But so then we need to move this vertically. So this is in the numerator, so we need to move it to the denominator. So we're going to do 1 over the square root of 9. And what is the square root of 9 going to be equal to? Well, that's going to be 3. So we get 1 over 3. Okay. So the tricky part with that one is just negative exponents, you just have to flip them, move them vertically, okay? So basically, we put this over 1, and this moves to the denominator, and once it does, it becomes positive. This becomes positive right here, okay? So once you move a negative exponent, it becomes positive once it moves from the numerator to the denominator, or vice versa. All right, well, we have number 3. We have the cube root of negative 8. We already talked about that one earlier. Cube root of negative 8 is negative 2. All right. And the last one we have, this one's a little bit trickier. We have 81 to the 3/4 power. This one will take a little bit of finesse, but it's actually kind of a cool process here. So let's rewrite it in radical form. So for these ones, we're not using a calculator. I would write them in radical form. It's going to make it easier to see stuff. So we have a 4th root, and we have 81 to the 3rd power. Okay, so I don't really know what 81 to the 3rd power is. That's going to be a really big number. But what I can do, I'm going to rewrite this. I'm going to show you how I'm going to rewrite this. I'm going to write in parentheses the 4th root of 81. And I'm going to move that to the 3 outside like this. Okay, that's a legit move. We can totally do that. Now, how does that help us? Well, if you look, do we know the 4th root of 81? Yes, we do. The 4th root of 81 on our perfect card is actually 3. So I can rewrite this as 3 to the 3rd now. And what is 3 to the 3rd? Well, that's 3 times 3 is 9. 9 times 3 is 27. All right, so it's kind of like our exponent properties and radical properties. It's kind of just moving stuff around and kind of tinkering with it a little bit to make it work out. All right, we have 2 more examples. Let's get to them. To solve each equation for all of its real solutions, if necessary, round your answer to 2 decimal places. Okay, so number 1, we have 6x to the 4th equals 3,750. So first things first, we need to get the x to the 4th by itself. Is it by itself right now? It is not. How do we get rid of that 6? We're going to divide by 6 on both sides. So we have x to the 4th equals, and then 3750 divided by 6 is 625. Okay. Now, how do I undo something to the 4th power? Well, I do the opposite root, which is going to be the 4th root. I'm going to do the 4th root to both sides. Okay. If I do the 4th root of 625, well, that's a nice number we know. That's actually going to be 5. The 4th root of 625 is 5, but we have to be careful. When we take a root of an expression or an equation that has something to the 4th power or to the 6th power, something like that, we're going to need the plus or minus, okay? Because there's actually 2 answers that work. With even exponents, that you take the 4th root or cube or whatever root you take of even exponents, you're going to need the plus or minus for this one, because it's going to work out, okay? Because if we do, for example, if we do negative 5 times itself 4 times, you can see that's going to equal positive 625, okay? So we need the plus or minus for this, but for odd number x's that we're solving for, so if we had x to the 5th power, you would just do the positive, okay? So you got to be careful with that. With even ones, you're going to do plus or minus because they will work out, like this one did here, but odd number exponents are not going to be, they're just going to be the positive one, basically, unless it's already a negative, I guess. Like before we had that negative cube root of negative 8, well, it's going to be a negative then. It's only going to be one sign, basically, is what I'm trying to say. Okay, one more example. We have the quantity of x plus 1 cubed, or for the 3rd power, equals 18. First things first, is the x plus 1 cubed, is that thing by itself? There's not like a 4 in front of here or anything. It is by itself. So how do we undo, we need to get that x plus 1 by itself. Now, how do I undo cubing something? Well, I take the cube root. Okay, so now we're going to have x plus 1 equals, and we're going to have cube root of 18. Is cube root of 18 a nice number on our perfect card? It is not, so I'm just going to leave it as cube root of 18. And then how do I solve that? I need to get that x by itself, so I'm going to subtract 1 from both sides. So I get x equals negative 1 plus cube root of 18. And I just did the plus here. I didn't do plus or minus because it's a 3 is a odd number root. It's an odd number root, so we're not going to need the plus or minus. And if you were to do the approximate version of this, it'd be approximately, when you add that in your calculator, you're going to get 1.62 approximately. So that's the exact answer on top, and the bottom answer is going to be our approximate answer. All right, and that's all I have for you today. Thank you for watching. Have a great day, and we will talk soon.